It's a really unique time because this is one of the first few colloquiums we are having after a long time here. So great to have a speaker like you join us today. So it's my great pleasure to introduce Professor Piet Van Mieghem. Hopefully I didn't butcher the name. He's a professor at Delft University of Technology and the chair in the telecommunication networks and chair of the section on network architectures and services. And I believe this has become a chair of network science recently. He has done amazing work in network science. I can read through his biography, but I would say that something that certainly inspired me and many others here are his books. One of the books for sure, on graph spectra and complex networks. He has written 4 different books. He did his PhD in Belgium, in KU, a very well-known school. And he has been working in network science now from 1998, as I can tell. And today he will talk to us about his work over the last maybe 10, 15 years, he's saying, in network science. I'm really eager to listen to the talk. Turns out that some of his colleagues are also connected to our students and postdoc here, so which is even better. So thank you very much. Welcome, and welcome to you, too. Thank you.
Very much. Thank you to you for the invitation. I'm very happy to be here in Virginia, and it's also my first talk in real since the beginning of COVID. So I'm going to talk about epidemics on networks. The last words is probably important, and I'm going to show what is a network. First, tell me from a network science point of view, what is a network? Yeah, a network consists of about 2 ingredients. The ingredient that you most know is basically the graph, the structure. I call it the hardware, the topology, whatever. So that's intuitively the easiest part, I would say. However, the other part, the function, the service, is equally important because that's the part why we actually design networks. And generally, you can say that networks are designed for, on a high level, to transport items from A to B. Yeah? It's a diffusion, it's a transport, and you use the underlying hardware or infrastructure. So, and that's an important thing. That's the duality, what I call, between the service or the function and the topology. And that, I think, it's a crucial thing in network science. Network science is not only graph theory, but also the processes that function and run on the graphs. That's an important thing. The second, I come now back to graphs. There are 3 big equivalences in graphs. The first one I call the topology domain, and that's probably the most intuitive domain we have, where you actually represent the graph by nodes and links. And you see it here. I got an example of a 6-node graph. You have 6 nodes and 9 links. The interesting thing is, this is the visual picture on which we as humans are very strong, and the way in which you then define, in most terms, the graph, that's by the matrix that we call an adjacency matrix. What is important here is that I'm talking about the underlying graph, topology structures, and I only talk about link existence. Link existence means you have either a link between 2 nodes or you don't have. And that's what you see here in the topology or in the adjacency matrix. You see a 1 for a link and a 0 if there is no link. Why do I stress this? All the links are here then undirected or bidirectional. So there are no directions of the links in a graph. And that's also because we talk about linked existence. It's just the process that will steer things. And there you have the direction of the links. As a matter of fact, you see here that this matrix, because it's undirected, it's symmetric. And a symmetric matrix, that's what we like. Because a symmetric matrix has a very unique spectral decomposition. Unique in the sense that you can always write a symmetric matrix, a real symmetric matrix. I'm not talking about Hermitian, but a real symmetric matrix. And this decomposition, where the X, the capital X, is the orthogonal eigenvector matrix. Within the columns, you have the eigenvectors. And in the lambda here, the capital lambda is the diagonal matrix. And on the diagonals, you have only the real eigenvalues. That is important because if you don't have a symmetric matrix, you end up with a much more complicated decomposition. Important what I was saying is it's symmetric matrix, then you have a reasonably elegant and nice decomposition into an orthogonal matrix, the X matrix, and the lambda matrix with all the eigenvalues on the diagonal, they are real, and so on. And then I also introduce a third equivalent representation, and it's the geometric representation. The geometric representation is that any undirected graph can be represented as a simplex in the n-1 dimensional space. So it means that all the nodes are now the edges of my simplex because it's a geometric structure, right? And the simplex is nothing else than a generalized triangle. If you have a triangle in 2 dimensions, it's just a triangle. In 3 dimensions, you have actually a tetrahedron. And what is interesting here is you can think about a graph as a geometric concept. Well, let us, these were the 3 equivalent representations. Why are these important? Because you don't lose information if you go from the geometric domain to the topology domain or the spectral domain. There is no loss of information. So this here is not a simplicial complexes in which you lose information. This is the entire information and the characterization of a graph, but in geometric terms. And it's still actually quite open to further exploration, I would say. That you can think about network as having angles, altitudes, centroids, a volume, and these are unique, right? It's a unique simplex for any undirected graph. Okay, let's now move to the epidemics. Most of the papers or most of the modeling in epidemics consist in the idea of having compartments. Compartments means that, let us say, we have a closed population, and in a closed population, the items, which are then most of the time persons, can only be in one of these compartments. And that's an important assumption, modeling assumption. It simplifies this thing. And I'm going to finish or focus here on 2 major distinguishes with compartments. Those that have actually a single realization, a single disease, right? The most well known is SIR. People started, most of them, to be in the green, susceptible, healthy. And then there is, you move to the infected compartment and then eventually to the removed compartment. Look here, we have now moved from the underlying structure. You have a contact graph. We are now talking about the epidemics as a process. And you see arrows. Yeah? There are arrows in the way through which the compartments we move. And that's an important thing, right? The other one of the major compartments is disease with reinfections. And reinfections, again, the simplest one is SIS. And where do you see reinfections? Because you return again to the initial compartment. Why is this important? You see actually here again a graph structure. Yeah? The first one is actually the structure of a tree. Yeah? You move from one to the rest, and this is a line, actually a line topology, but you can have splits offs and that you have a tree in a one single, while in the reinfections, you have actually a graph, you have loops, and from a just graph theoretic point, yeah, you know that reinfections will appear most of the time, because in a graph, you have easily loops. Yeah? So, and probably that's also a general way, if you see an epidemic, that reinfections are also very common. And you see it with COVID too. Initially, people thought, oh, COVID is only in one direction and then we are done. But now we see that many people can get reinfected. Okay, this is the epidemic compartment. And then the last, this is still my introductory slide. The last one is actually that epidemics belong to a very common natural class, which are called local rule global emergence effects. And what is this? Again, we start with the underlying graph, which is a contact graph. It's given, let's say. And in the contact graph, on top of that, we have the process graph. And in the process graph, each of the items, I call it items, might be persons, they just focus on one particular local function. And the local function means that you only interact with your direct neighbors, not with the rest in the graph. Like, for instance, in epidemics, the simplest one is an if-then-else rule. What you do is, once you are infected, and here infected is in red or in orange, and healthy is in gray. Once you are infected, until you are recovered, you just do infect your healthy neighbors. So in this example, this infected node can only infect this, which is a healthy neighbor. All the rest are already infected. Yeah, and that's a very simple rule. The amazing thing is that the simple rule can be written in one software program, and due to the interconnection of the underlying graph, yeah, you can have an amazingly complex global emergent property. That's what I call it. And one of those examples are, yeah, you can have a flock of birds or a swarm of fishes The local rule is always more or less the same and simple. The fishes stay at a certain distance from each other and take the same velocity. That's the only thing they do. And still the swarm can have an amazingly complex behavior. And you will see that the complexity in the behavior is also in epidemics, and it's an essential thing. Okay, let's now move to this was an introduction. Now I'm going to focus on the theory, the essential theory, a little bit of epidemics. Then I'm going to talk about recent developments, on which I say something about a non-Markovian and interfering the contact graph. So let's start with epidemics on networks. Well, this is probably a little bit too easy all for you, but let's start with a confinement. I just looked to the simplest cases, and I look to SIS virus spread in a network, and I start with a given thing at time 0. I assume, and that's important, I assume that I know the underlying graph, the contact network, and I know that at least one node is infected, otherwise nothing happens. Yeah? And all the others in black and white, they are not infected. That's the given situation at time 0. Then I'm interested in the question, the focal question, what is the probability that one of these nodes, say node K or M, is infected at time T? That's what we want to compute. The other question might be, like, how long does it take before I get infected? Yeah? So you have two different high-level questions. That's the probability to see in a population who will be infected. And the other one is the time-related one. When will somebody be infected at some time? Before I start, it's always good to have the assumptions, because here I have a lot of assumptions. The first one is obviously the simplicity of the compartment model. I only assume 2 compartments for simplicity. The second one is that I assume that the complete graph, the underlying contact graph, is given. I know all the details, and it is constant in time. And then I assume also for simplicity that the processes on the graphs are simple ones. These are Poisson processes. And the Poisson process is actually a very random process. Once you know that something has happened in a time period, yeah, you only know that it can happen at any time uniformly between that time window. That's Poisson. That's the most uniform process you can ever think of. Yeah? And if you don't know anything about virus or spreading, that assumption is not so bad. So I assume that there is an infection process, and the infection process is going only over the links, and it has a strength beta, and that the strength might depend on the 2 nodes. It might depend in general. And then I have a curing process, and that's only a strictly nodal process in which I myself cure independent of the curing processes of somebody else. And in reality, that's actually fine, because most of us, yeah, you get in a healthy state just completely independent of any other patients in a hospital. So the independence of the Poisson processes is more or less realistic. Now, to go a little bit further, I assume that those strengths here of the process are also constant. They do not change over time. That's a very big assumption, because normally your strength and the infection strength, everything changes over time. But here, everything is constant. So the beta, the strength of the infection process, and the delta of the curing process is constant over time. Okay, good. Then how do we solve the problem? In general, we assign to each of the nodes a health state. And the health state is written here by a capital X. And capital X is viewed as a random variable. A random variable is actually something ugly. It's a little bit difficult, but okay, a random variable basically means that as a function of time, my position can be either infected, and then I'm in one state, I remain for some time in one, then I get healthy again, I get reinfected, and so on. So you have actually a binary, if you wish, a kind of a binary sequence between 0 and 1 over a very long, well, over a long time period. And what we are interested in to compute is that is just the probability that I'm infected at some time, and that probability equals 1. That is what we were going to compute. Before going further, an interesting observation is the following. If you stick to SIS, you see that your random variable can only be in 1 and 0. A random variable that can only be in 1 and 0 has a very prominent, nice property. It's called a Bernoulli random variable. And the strong property of Bernoulli random variable is that the probability, which is a difficult operator, be honest, that's difficult to work with probabilities, can be replaced by a simple linear operator, which is just the expectation. And the linearity of the expectation, that's great. We will see that later on. Okay, so this is virus spread. I've defined the entire problem due to the fact that we have assumed independent Poisson processes, and I assume that you know a little bit about Markov processes. You can sit back and think, okay, due to the assumption of Poissons, all independent, probably Markov theory can be applied. And a general rule in stochastic theory, if you can do it with Markov, you should. There are only, Markov theory is a very strong theory, although it might sound sometimes a little bit complex. So here I solved the problem for a very small graph, graph with 4 nodes. And you see here the 4 nodes are written by dotted line. This is now a full mesh. They are internally all connected to each other. And coming back, this is my structure and my graph. This is the underlying contact graph. The whole process, the function, the epidemic diffusion, if you wish, or the epidemic spread in SIS, has this kind of a Markov graph, which is way more complex. And what do you see? You see here, first of all, we have only 4 nodes, 4 persons in the contact network, which actually means that you have actually a state or a dynamic state of 2 to the power n states. So it means that my Markov process, my diseases jump over all these states, and in each of the states happens something, right? So, and what are now the states? I draw it here in 5 layers. This layer is the network state in which all the nodes are infected. And the binary, well, I use here the binary, the digits is the binary number of, this is a digital number and this is the decimal notation. And here you see on this layer, all the nodes in the network, 3 of them are infected, 2 of them, 1 is infected, and then the one above, none of them is infected. That's all quite logical. What you also see again is arrows. These directions are bidirectional. So the Markov process can jump either 1 level up. So it means that there is 1 more infected. Suppose we are in 13. So the 3rd node is here also infected and all of the nodes are infected. Or it can jump, there can be a curing, and each of these 3 nodes can cure. And if they cure, you have, here is the 2nd node cured, here is the 1st cured, and here is then the last cured. Yeah, due to the digital numbers, this is just a kind of relabeling. So these links are undirected, except for the state above, which is an absorbing state. It means that once you're in the absorbing state, you stay there forever. Why? Because the virus has just disappeared from the network and you are actually in the steady state. That's the state in which we eventually will always come. Eventually, because in any Markov process you see, if this is the precise Markov graph, it is asymmetric. Yeah? You can come many times in the all healthy, in the all infected state, but you can come only once in the all healthy state. So, and the Markov process jumps with the probabilities of the links on these. Well, I didn't show them because otherwise it gets a little bit messy. But eventually there is always a probability that I hit my absorbing state. So the final state is always the absorbing state. That is what you learn by epidemics. So in short, coming back, we've solved with Markov theory our simple problem of SIS, and we end up with a complexity which is exponentially large in 2 to the power n linear equations, because Markov theory has linear equations. So I have a huge system of linear equations to be solved, but the system is so huge that even the best computers cannot do it. And that's already one of the things which is coming up and pointing to the fact that your underlying process, think about your local rule and emergent properties, is a very complex one. Yeah? We will know, and we know a phase transition occurs. And phase transitions are very difficult things, but this is an exact description also of the underlying phase transition. The last thing what I wanted to say is that the rates here to move from one state to another state are in the large infinitesimal generator in Markov theory and are function, of course, of the underlying graph in a complicated way. But anyway, this is the first solution, and you can go to a computer, you can solve it, but it doesn't give you so much insight, right? The only curious thing that I still mention is that the degree of each of those nodes is always 4, equal to capital M. So it's a regular graph. That's amazing, right? This is a regular graph. And you see, it's one of the very few problems in dynamics in which you have 2 types of graphs. You have the graph of the structure, and also the complete dynamics is a Markov graph, because I can use Markov theory. Yeah? So I have double the strength of network theory, if you wish. Okay, it doesn't give you so much insight. Now I'm going back to the original binomial, the Bernoulli random variable, and I give you a physical approach of what's happening. So this is an ugly, big formula, but it's easier than you think of. So we start with the left-hand side. The left-hand side is in Newtonian thinking that we always try to see if you have the present state, you want to say something of the state t plus delta t, at time a little bit lost, and then you make the delta t so small that you actually talk about the derivative. Yeah? And what we say here is that the time derivative, we are interested to understand what is the time derivative of the probability of infection. And here I use the fact that we have Bernoulli random variables, meaning that I can replace the difficult operator of probability by an expectation, which is a linear operator. And the linear operator is fantastically written in the right-hand side. Forget the linear operator in the right-hand side. Yeah? And then you can just function and reason on the physics of what's in between my expectation brackets. Because what's written there? I have here a Bernoulli random variable, and here I have minus that Bernoulli random variable. Okay? So I have 2 rates. First, focus on the first one. If I'm infected, so this random variable is 1, this one is 0. So I can ignore that term. I only focus on this term. If I'm infected, what happens? I cure with a rate delta, and it must be a minus sign. Why? Because my probability of infecting gets smaller by having me cured. Yeah? If I'm cured, the probability of infection is smaller, so a negative sign. The other thing is, if I'm healthy, then this term doesn't appear. Yeah, it's 0. And only this term is 1. And what happens? If I'm healthy, I will get infected by this term. And that is the sum of all my neighbors that are infected. They should be 1. Infected, the Bernoulli random variable, all my direct neighbors, and they all have a strength beta. Yeah, and they infect me. I assume that here all the neighbors have the same strength. If they don't have the same strength, then I bring in the beta inside the summation sign. But for simplicity, this is already fine. So this gives you always, this is a perfect description of the local rule. Yeah? If you program the local rule, it is an if then else. And this is nothing else than an if then else. If I'm healthy, this does not matter. If I'm not healthy, then the other one doesn't happen. So due to the fact that I use Bernoulli random variable, I have a precise if then else implementation in analytics, which is not so easy. And then the other thing what I'm doing is I multiply out my random variables, my x, I move in the linear operator, the E operator, the expectation operator, and I end up with this differential equation. And what do you see in this differential equation? You see obviously one complication. And the complication is in the last term. Why? The last term, we see that there are joint probabilities going in, while I only write the differential equation in the single probabilities. Not a problem. We can do the same exercise and can restart and think here about what is the difference or the time derivative of the joint probabilities. I can split off the joint probabilities, which are a pair of nodes, and I can write that also down here. Believe me or not, we did it. And you end up then with a term here with the triples coming in due to the connection with the networks, and so on. You can write in the triples and then the quadruples come in, and eventually you end up with a system in which these terms disappear, but you have a lot of terms and precisely equal to 2 to the power n terms, what you have directly for Markov theory. So what you can say is, Markov theory is great. It gives you the exact solution. Why do you do all those things? Well, having this equation gives you some physical insights, because we know we can't solve a system of linear equation from 2 to the power n. Yeah? Because if n is 10, then we have thousands equation, but if n is 20, we have 1 million equation, and the population of 20 is still small compared to what we are interested in. So one of the first things is, well, this exact solution, we approximate it, and one of the most famous approximations, what you do if you have a random variable, yeah, and you want to get rid of the random variable, you just ignore and you replace the random variable by its mean, and you hope that the mean is a good representative of the random variable. So I've now written the same exact general equation, and now I've written the sum of the neighbors in the adjacency matrix elements. So here you see the network coming in an explicit way. Then I replace the random variables by their mean, and I replace it by the mean, and then it means actually I replace it by the approximation of the mean, because it's not the real random variable anymore, because I'm making approximation. And then by doing this, I end up with deterministic equations, because my W is just a real number. And I see that the equation is now here, the complicated term due to the network, it is quadratic. It's a quadratic, it's a non-linear differential equation, while originally the set of all the 2 to the power n differential equations were linear. So and this is what I call the NIMFA approximation. Why? I still like it because it's NIMFA is a Greek goddess and it's a beautiful girl. So it's fantastic. It's a very powerful way. It's a basic way of doing mean field approximation, and it works better and better if the system is larger. Another thing what we can do is, if we focus on this equation, is a little bit mathematics, and mathematics in the simple sense. Yeah? So I wrote that equation again. Here you see the matrix elements, and then I substituted here the probability operator by my VK, which is a real number. Okay? And I said already that this term here is a complicated term. But if you look to the complicated term, this is a joint probability, which lies between 0 and 1. The adjacency elements are 0 or 1. And then the beta, the infection rate, is also a positive number. So what I wanted to say is that this complicated term is always positive, but there is a negative sign before. So if we get rid of that last term, we end up actually with a matrix. Well, I wrote this for all the components because this is only for node G, but if you write it for the whole network, then you have here the vector, which has all the components V sub G. And then you have here an equality, because this term is ignored. So the first two terms are actually an upper bound. And that inequality is a linear equation. Yeah? And I wrote it in a matrix equation because if you write that sum here, and there's a vector, and then over all the lines, you end up with a matrix, the A multiplied by the capital V. And there you see suddenly that the whole matrix, the adjacency matrix, pops up. This is a linear inequality. We can solve this. Most of you have seen that. So it means that at a certain moment of time, the infection probability vector depends on the initial condition multiplied by a matrix before that. And the matrix before is an exponential of the adjacency matrix of beta times the adjacency matrix minus delta I. Important is that this matrix here is a symmetric matrix. The E to a symmetric matrix can again be decomposed, and I wrote it here down in an eigenvalue structure because the eigenvalues are real. And then because it's an exponential term, yeah, the most important one is the first term. And all these terms here are the outer products of two vectors, the eigenvectors, and they have the same norm. They have the norm 1. So the important term in magnitude is the exponential factor. That's probably important to understand. Then you can look to this exponential term in two regimes. There is a regime that the exponential terms start increasing with time, and that increases with time if and only if the largest eigenvalue here is larger than 0. If that is larger than 0, right, then we have an increase over time. What does that mean? So it means that initially here, an epidemics can increase as an exponentially fast. It can never increase faster than exponentially. So this is a simple proof that's saying that whatever exponentially can never explode, it can only grow exponentially fast, right? And initial, I said, because after some time, that exponential will be much, much larger than 1, while this factor is bounded by 1 because they are probabilities. Yeah. So this bound is probably not so interesting only in the beginning to tell to people initially it can grow initially exponentially, but then it must grow less. Probably more important is that if your large term is smaller than 0, so as a function of time, my exponential term or the right-hand side decreases. If the right-hand side decreases exponentially fast, and it's an upper bound, then it means that my real epidemic or my probability vector will decrease even faster because it's upper bounded by a changing exponential. So what did we learn actually? What we learned is there is a regime in which this is precisely 0. And if it is precisely 0, we call it actually the epidemic threshold. You can solve those equations and you can say that the effective infection rate, which is beta divided by delta, by definition, is smaller than or equal than 1 upon the largest eigenvalue of the graph. And that is what we call the spectral radius. I equate this one equal to the epidemic threshold minus to the power 1. And the power 1 is actually the first mean field approximation. And the first mean field approximation I've just shown to you, I called it NIMFA. Why is it the first mean field approximation? Because I have actually substituted the random variable by the mean. Higher order mean field approximation can only replace then the joint probability by a product of 2 probabilities and so on. So that's the second order, but this is the first mean field order, and you can show also that the epidemic threshold indeed in NIMFA is precisely equal to 1 over the largest eigenvalue. The whole reasoning why I give it is important to some extent because it shows that the real epidemic threshold must be higher than a mean field epidemic threshold. Why is this? Because here I deduced the mean field epidemic threshold, but that's an upper bound. So once this regime is going already in decreasing mode, the regime here is already much smaller. So the real epidemic threshold is always larger than the first mean field or the NIMFA epidemic threshold. And that's of huge importance because if you engineer a system, right, and we focus here on the worst case, we are always safe. And what we want, of course, to do is that we want to have the epidemic threshold as low as possible. Another thing, the epidemic threshold is probably more in physics, but if you go to epidemiology, people like to have actually the relation between the strength of the virus, the effective strength, divided by the epidemic threshold. And that's the ratio, and that ratio is tau multiplied by the spectral radius, and we call this the basic reproduction number. And the basic reproduction number, that's what you read in most of the papers and also newspapers. And where does it come from? You have the prevalence, which is then the average infection rate over all my nodes. And then you do a little bit of math, and then you find actually that is the exponential, the R0 minus 1, multiplied by the time, and now the time measured in averages of the average curing rate. Okay, this is the mathematics that I'm showing. Then now I don't show too much mathematics anymore. I will repeat this equation because it's actually a very nice, simple, well, apparently simple equation, and it can explain a lot. Let me see now. Here on the left axis, I have the prevalence, which is the average fraction of infected nodes, versus the effective viral strength. And we computed it with NIMFA. This is the approximation, the mean field approximation. That's in a thick line. And the other lines are the exact solutions of our Markov process. And there you see if the topology is small, then 25, for instance, is relatively large from my NIMFA bound. If it's 50 or 100, I come closer to that form. That's what you see. You also see that, of course, there is then the 2 phases. Yeah, the 2 phases. The one phase is that the virus on the long term, after enough long time, it exponentially decreases and the virus is extinct. And on the other hand, the virus stays in the population for a very long time. We also show that the point here, where we have the epidemic threshold, significantly depends on the underlying structure of the network. And then you can actually normalize your axis in terms of tau multiplied by the spectral radius, and that's nothing else than the basic reproduction number. And if you look to the basic reproduction number, you see the same duality between in a network. You see the process is given by the tau, and the structure is given by lambda. These things are inherently, and you see it also in the dynamics. Okay, so this is actually in a nutshell what I think are the essentials of epidemics. Of course, this is a very simplistic view, and probably the largest comment that you might have is, you have only two compartments. Reality is much more complex. You have a lot of departments. And here I wanted to stress the work of the group of Katrina Scoglio, where actually an extension of NIMFA has been done to multiple compartments. And to some extent, the basic underlying theory really says the same. Of course, the complications due to the many compartments, because you replace a simple line topology by a more complex topology, it can still be done. Good. Now I come probably to the more interesting point, because the theory you knew for a large deal. And I'm now going to talk about recent developments, which I think are interested, at least I'm interested in them. And I talk about non-Markovian, and a second thing about the underlying compact graph. Let me first start with non-Markovian. In the beginning of COVID, we got data. This is the first wave. These are the times. This is the prevalence, the number of infected nodes, as a function of the time measured from the first, well, in the Netherlands, officially, the outbreak was somewhere in the beginning of February, and then the times when we got already in lockdown. Right? And lockdown means in a certain regime in which I hope that the dynamics are a little bit stable and not changing too much. And then we got here the functions, the data in the bullet points. And what we did is with the data, we tried to fit the data with all kinds of distributions. You see Cauchy distribution, the Gaussian log normal, the secant hyperbolicus, which is actually the underlying SIR distribution, and also the Weibull distribution. And guess what we found? I was looking to the exponential decay, because Markov theory, what I've said to you, that's exponential decay. We've derived this kind of a function. And so in the deep tails here, large enough, if this is negative because I'm dying out, then I should have a linear regime. This line here in blue should be on a log length scale. On a log length scale, it should be a line. And actually, we found that it's better fitted by a log normal. And that is not only the data in the Netherlands, but we did it in 10 other European countries. We got the data, and they were all pointing more or less not to exponential, more to log normal, long tails, not very precise. And of course, I should add one thing. From an engineering point of view, these are extremely bad data. You should never try to make a conclusion, because you see that all these different distributions more or less are fitting the data. You cannot say, well, one of them is better than the other. They are all equally probably bad. So then I thought, well, that's probably not a good way to look to the question, what is now the infection? Is it Markovian or not? Therefore, we started to look to Twitter epidemics. And Twitter epidemics are much more precise. Let me explain what we do. Here in Twitter epidemics, we start having more than 10 million of Twitter retweets, I would say. And we consider that it's epidemically spreading if somebody retweets the news, because then you're spreading the news over the whole population. And we try to see what are the delay components. First of all, you have actually 3 delay components. The first time is on your machine, you type Twitter, you send it, and then it goes over the network, and this is milliseconds. Actually, this first component you can ignore. The longer components are those by the humans, because now it comes on your machine, it gives a beep. Some people immediately read. Other people, they know there is a beep, but they read the message after a time T2. And then if they have written, they need another time to think, well, was that a good news or not? Should I retweet or not? And then that's the reaction time. So we have actually 2 times, that's the observation and the reaction. And these times you can measure from retweets in Twitter, very accurate. And we did that, and we plotted now the total time, which is actually the spreading time, because here I'm infected by the news, and here I infect somebody else by the news. That's my capital T, that's the infection time, what I wanted to understand what it was. And then we measured that, and we found out, well, the blue line are the measurements, which we go to 10 to the minus 7, meaning that we have approximately 10 million data points. That's okay, this is conform. And we found that the function what we fitted here is precisely a convolution of 2 log normals. And we find that the human behavior is log normally well distributed, as well as the human reaction. That was actually an amazing thing to support, probably humans react in a log normal fashion, because this fit is, in my opinion, quite overwhelmingly accurate. You can always say, okay, it might be a little bit still an order distribution, but roughly it might be close to a log normal. And this brought me to the idea a log normal is very far from an exponential, so Markovian thinking is skewed. It might be very erroneous. We assume just exponential infection time in Markov theory. That is not the case. So then what we were thinking is, okay, let us see what is the influence of non-Markovian infection time on a Markovian process. And there we started having the Weibull distribution. And the Weibull distribution is given here by the shape parameter alpha. Why is the shape parameter alpha important? Because if you take alpha equals to 1, we have just a simple exponential like in Poisson or Markovian theory. And this is just the exponential. So the alpha 1 case is our benchmark case. Because then we know alpha 1 complete acceptance of Markov theory, and we can then compare if we have a smaller or a larger shape parameter. So, and that's how the distribution of a Weibull looks like. So the infection time is the time to infect neighbor. That's given here. That's the probability distribution. You see in a thick line, the alpha 1, which is precisely our exponential. And if the alpha is smaller than 1, then we have the blue curves. If the alpha is larger than 1, we have the green curves. And in order to do a fair comparison, we assume that each of the Weibull distribution had the same mean. And by having the same mean, it means it must be having the same mean as in my Poisson. It must be 1 over beta, because 1 over beta is the average infection time. And by having this imposed, we could get rid of the B parameter here. You solve that equation, and the B parameter is then incorporated. In any way, we can then compare the Weibull infection time with the Markovian or Poisson infection time where alpha is 1. And guess what we found? We found actually in simulations that in the black line, you see Markov theory. If the alpha is larger, we are in the nice regime, because then my epidemic threshold is shifting to larger values. So the larger the effective epidemic threshold is, the best for us. However, if alpha is smaller than 1, we enter into a more dangerous regime. Because if the epidemic threshold gets close to 0, it means there is no barrier anymore for the epidemics, and the whole population gets swamped by the virus. So this is the regime, smaller alpha, which is dangerous for a population, right? So this brought us actually to the fact that even if you're going to compare in the Markovian theory the underlying graph structure, the deviations on the underlying graph structure is smaller on the epidemic threshold than the non-Markovian effect. So that was actually a triggering that I thought, okay, the Markov theory is probably a little bit too simplistic to be completely true. And here we computed this. Well, okay, the reason why I gave this is a little bit far. This is the line with 1, alpha 1. Alpha 1 is the epidemic threshold that I just computed. That's 1 over the spectral radius. If alpha is larger, right? Larger means that my epidemic threshold may be much larger. And then by doing the theory, you can actually figure out that the first term here, or 1 divided by the logarithm of 1 plus the spectral radius, is the maximum possible that you ever can have. Because that means if alpha goes here to infinity, you just have a delta function, meaning that all the nodes in one time, they all get infected, they all fire, and that's the best case for an epidemic. What you also see is that if alpha is smaller, the shape factor is smaller, the epidemic threshold, because that's the epidemic threshold here, goes down rapidly to 0. And that's the dangerous regime. What I did in my Princeton time, I started again with thinking about the Chapman-Kolmogorov equation and Markov theory. And you know, I said this already, this is a linear differential equation. This is my infinitesimal generator, which is the weighted minus the weighted Laplacian of the underlying graph. The S is my probability state vector. And this is, well, the governing Markov equation. Why is this an interesting equation? Because you can have an exact solution, and the exact solution is the exponential that I've used. And at any moment of time, you can basically compute in a network, given the network is there and the infinitesimal generator is constant over time, then I can at each moment of time precisely compute for each of the nodes what is their probability state. Now, what I did, I've replaced the differential operator by a fractional, a Caputo differential equation. Don't worry if you don't understand it. That was also new to me, but you can actually go to fractional derivatives. The nice thing is you write that equation becomes here with alpha, and I think also in the infinitesimal generator in alpha, that's all the mathematics. What is important is there is an exact solution. And that's why I was triggering for. And the exact solution is written in terms of Mittag-Leffler functions. These are the Mittag-Leffler functions. You're from Sweden, not from Norway, and these are quite complicated functions. The only thing is, if alpha is 1, you put it in, you get the exponential. And of course, it should be the exponential because that's my Markov theory again. Yeah? There are a lot of problems here. Yeah? But one of the things, what is interesting, what I found interesting is that the Mittag-Leffler functions, and I draw this for you on a scale, linear scale, and I compare them with the Weibull distributions. And then you see the Weibull is in red and the Mittag-Leffler is in blue. And you see that they are very, very alike in realistic regimes of the parameter of time. But there is one surprise which makes the theory so annoyingly complex is that in the Weibull distribution, all the moments exist, but none of the moments exist in Mittag-Leffler. Why is this? If you look to this scale, you say that is impossible. Right? It was my first reaction too. Therefore, I made another plot, and I plot here the distributions on the log scale, and here in the time range, which is still a reasonable time range. And of course, you see a little bit of difference, but they are still reasonably close. However, if you take here a much longer time scale, like 10 to the power 10, then you see basically that there is a cutoff. So the Weibull distribution has an exponential cutoff. It makes all the moments existing, and the Mittag-Leffler function stays in a power law regime, and none of the moments exist. And that's a major complication for the theory, but I'm more excited to the fact that in a realistic time regime, these Mittag-Leffler functions and the entire linear theory still applies and might be a better approach to non-Markovian epidemics. Okay, my last point is talking about the graph. These are again data from the RIVM, which is the Dutch CDC, as a function of time in COVID. And we've created actually a kind of prediction algorithms, which we think is quite close for the mean of the prevalence. What we did, our underlying structure is we took into account all the provinces in the Netherlands, so a little bit the topological structure, and that gives us the possibility to do the prediction which you see in yellow. But that's not why I showed that picture. This is a picture where you see that you have several waves or peaks of the epidemics over time. This curve here is also a very annoying curve because you can't see any structure in the curve. And now what I was thinking, okay, this curve is basically the curve what everybody wants to know. Yeah? Because if we knew the future at this time of case, we would have been much more effective in reducing the number of infections. Yeah? If you look to this graph now, this gives you the epidemic, the prevalence as a function of time, but in several sequences. In each sequence here, the underlying graph is constant. It doesn't change. All my epidemic parameters are constant. They're all constant. And then in this regime, the underlying graph changes again. In this regime, and then it stays constant, it changes again, stays constant, it changes again, stays constant. It always changes. It changes at the times here, the line, and then it stays constant. And then, if you see, you can compute for each of the nodes in the network. These are the blue lines. They just concentrate on the red line, which is the prevalence. And then you see that the prevalence is going up and down and so on. And actually, the prevalence is steered by the R0, because the R0 is, this is constant, this tau, because my beta and my delta is constant. And you only see here the effect of changing the underlying graph. If you change the underlying graph, the spectral radius will change. If the spectral radius changes, the R0 changes. And you see in the different regimes here that the R0 has been changing. So we've simulated a lot of these changements of underlying contact graph, which changes the R0. And then you see, yeah, this is again some behavior. You can have this kind of behavior, and you can just mix it around. You can go back to this curves, and you can try to fit this curve with an underlying changing of the graph. You don't know how the graph changes, but you can find what is then the best spectral radius. And in principle, you should be close to this one. Then this brings me then to the crucial point. Yeah? If the epidemics parameters do not so change too much, but the movement of the people, that's another point of view of looking to an epidemic, because I can produce more or less the same curve without changing my compartments, only changing the movement or the process, how people interact. I found it funny, actually, that it's so close. Another thing what we did is, that was the question, suppose you have the epidemic threshold of the epidemic data over a long time, how can we actually find the underlying network? And that problem is a difficult one, which it's actually an NP-complete problem. You can only solve it partially. And what I do with partially, we show that you can actually here learn about the past state of the epidemics, and then you can predict for a quite long time, and your prediction is amazingly well, but unfortunately, you cannot say too much about the network. Why? Because your epidemic prediction actually is accurate by a couple of eigenmodes, while in order to construct the whole graph, you need all the eigenmodes. And here in a predictive system, an epidemic system has a very low dimensional system. It is like an autonomous system. I can talk a bit more about that, but you only have a couple of eigenmodes that are triggered by one single epidemic. So that's the reason why we could predict quite well, but we can't say too much about the underlying network. Okay, I said already a couple of times, I believe that the contact network is much more important than we now think. And I think, yeah, the difficult thing is, of course, measuring. Yeah? Simon Stevin was one of the famous guys in the Netherlands or Belgium, how you in the beginning of the Renaissance, and he said already, in order to know, you have to measure, because meten is weten. That's what's the meaning. So we also developed Corona app. That was my last thing that we did. We did a Bayesian estimator for tracing infection state. So it means that Betis, that's our algorithm, it learns over time, adapts an underlying epidemic process, and by learning, you converge very rapidly, at least in computer simulation. I found it amazing. You reach to the real infection per person in a network. There was interesting companies wanted to implement this, but he said to me, okay, just find government agency that wanted to implement and solve this, or find a lot of people that are willing to actually use this app. And here we stopped a bit because there was not enough societal interest due to reason. Actually, I was pretty much frustrated because I think we should develop these things to the future. So I come to my conclusions. I'm already quite low. I'm very fascinated by the theory of networks. Believe me, we have not seen the end yet, by far. I also realized that nobody can predict in 1% a few days ahead. I've had talked with a lot of people, an accurate prediction, and still this gives me some support that we need to measure something more than only the epidemic state, but also the way how people interact. Again, the contact network. Today, I find probably that too much money goes to the medical industry, and there is hardly money that goes to digital technology. Probably as engineers, we should probably try to change this a bit, and not completely. It's not a black and white, but I think that digital technology might help. And then the last thing, I'm very for freedom, but one of the things we need to realize is that freedom comes with an epidemical cost. It means that, and I try to show this to you, the spectral radius is a very sensitive parameter. Any change in your network, if you add a link, it will always be larger. So it means that any contact more has, well, an increase of the spectral radius and a decrease of the infection threshold. And this infects us all. Yeah? And the second thing, what I didn't have time to, is that anywhere in the population there is an infection, it will always increase your probability to be infected, which is quite logical, but not so easy to prove. Yeah? And those two things, I think, should come to people that are only thinking about their personal freedom. That's good and well, but you actually lower the freedom for all of us. So I'm going to conclude with this talk, and just probably a short, that I'm still looking for brilliant people to start an ERC project on virus spread, 5 PhD students and 2 postdocs. Okay, thank you.
Thank you very much. It was a brilliant talk. Questions from the audience? Yeah, go ahead.
So I really enjoyed the talk. Something which wasn't clear, so you had, like when you were trying to predict the cases, you had these segments, right, when you were inferring the network. Maybe I didn't understand how are you trying to learn. Right, so what are these segments? So like you have learned the graph and then...
No, not learned. Here I assume, I do a simulation and I assume that the contact graph is constant during this time.
Okay.
And here on this time, it can randomly change, right? And then it's again constant. But the only thing what we do is we show that there is continuity in the prevalence, not in the derivative, but in the prevalence. So at this point, a little bit to the left, the probability is the same as a little bit epsilon small to the right. And that's the gluing together of these differential equations. But the underlying contact network changes any so many random time we choose, and then it changes completely. And once the network changes, so the total adjacency matrix with n capital N nodes, the total number of nodes is the same, but the number of links changes, then we can compute from that matrix each time the lambda 1. If you have the lambda 1, you can reproduce the reproduction number because we assume that the beta and the delta do not change. And that's what you see in the changes here. And these are quite dramatic, these changes. And it should be because these two parameters are not consist of the multiplication of the epidemic part and the multiplication of the underlying contact graph. So they are, from a physical or mathematical point, equally important, if you wish. Well, equally, it's difficult to say equally, but that is what we did.
Thank you for the talk. It was really interesting. So I have a question about this result. So here, when you have changed the network, instead of all nodes, did you conserve that infected node in the first? For example, you have changed the network at time t5. So did you preserve the node state or you?
This is completely mean field. It's not a nodal state, but the probability of infection is it's constant, well, at both sides of the, at an epsilon time here and an epsilon time to the left. The probability is changed, not the state.
Okay. Okay. So that probability did you preserve and for the? Okay.
Yeah, because you are at a certain moment of time in the same state. But we didn't hear the state because in Markov theory, it's way more complicated to do these computations and simulations even.
Okay.
So this is just mean field.
So I have another question about the first order NIMFA. So when we get mean field first order approximation, like if we increase the order, like second order, third order, so it's like we are going to close to the exact, when we are increasing from first order to second order, so how much, and second order to third order, okay, is it linearly we are going to the, or is it non-linear?
No. Okay. That's a good question. You can best understand it by what I said here. Oh, completely in the beginning, that's the matrix here on this one, right?
Yes, yes.
So this is first order, and in order to get everything in first order, you need to get rid of the second order. And what first order mean field is doing, you say that the joint probability is nothing else than the product of two first order probabilities. Yeah, and this has the biggest effect. If you go to then the second order probabilities, in which here the triples are coming, you then do a kind of a closure, what people say, and you reduce the triple probability to either a single probability or a double probability. And your system of equation gets capital N plus binomial n over 2. So it's a bigger linear system already. And then of course, you should be more close to the exact solution because you take more information into account. But the steps that you do, because if you take a second order, then you have capital N equations plus binomial over 2 pairs equations. That's a huge thing. And that will also block you in the computation of large population systems. So to come back to your question, what is a very interesting one is, that is indeed the question whether it's possible. Yeah, but a first order mean field equation is better than a second order. That's an open question in physics and mathematics. Nobody knows. Rick Durrett thinks it might exist, but nobody has a proof. And that would be cool because then you can say, okay, don't go anymore to higher or second order because, well, my first order has abounded or is always better or and so on than the second mean field or the third order mean field. So that's still open.
So in some sense, this is like a inclusion-exclusion formula.
Right.
So that's why you can't, you get positive and negative terms. So you really can't bound.
Yeah. Well, here, okay, true. It's very close to inclusion-exclusion. Yeah.
Go ahead.
I have a similar question here. So, do we know that for a certain class of networks, this term that we are ignoring, third term, what is the order of that term?
That's also a very good question.
So, how close the upper bound is?
You mean the importance of this term?
Yes. Do we know that for a certain class of?
I don't know. That's a very good question. That's also virtually open. Look, what happens is there's a phase transition. A phase transition you all know very well. You have water and it freezes to ice. On ice we can walk, in water you just disappear. The same actually happens when you're coming close to the epidemic threshold. Then this term, the higher order terms, get of more or less the same magnitude as the first order term. So in some extent you cannot ignore them anymore. But the precise analysis is left to the young people. I think it's very difficult to do this, but it will give you information about what's really going on. Because actually what you can see is that your epidemic state is freezing around, well, freezing, it's not the right word, but that's the analogy with the phase transition. It's basically your epidemic is freezing and the pairwise might be equally important as the triple-wise as the single ones. And that's still an open question. Oh, by the way, I think that as far as I know in physics, there is only one analytic theory that computes the phase transitions. And that's by Ralph Onsager in the world. He got a Nobel Prize from that. And he actually computed in 2 dimensions the Ising model completely in an astonishing paper. Really, with elliptic function, it's a mathematical tour de force. But he calculated precisely what's going on in the phase transition in an Ising model. Ising model are these magnetic spins, and they all align around their critical threshold. They also have. And I believe, because the SES is still the simplest one, you have seen the complete Markovian graph. It's linear. It's only an exponential state space explosion, but there must be more information hidden behind. It's not easy, because otherwise it would have been done, but it's an open question.
Can we expect that as you go further in this decomposition, this eigenvalue, so for now, maximal eigenvalue is playing a role in the threshold. If you go one step further, second maximum value comes into picture, and third and so on.
Yeah, we once computed this, and it's indeed true that if you go to a first order, then you have 1 over the lambda of the matrix, which is an n by n matrix. If you go to the second order distribution, your matrix gets larger, and you can also again compute the spectral radius. And it is indeed, we found that that is always an upper bound of the first order. And so you can probably, that's intuitively, I didn't do it, only the second order, and then I stopped. But you can probably find a way to go to higher and higher orders and show that it is always increasing to the real epidemic threshold. True? Well, true, I mean, I expect that it might be true.
Yeah, I have a follow-up question with this. I'm not aware of the existing literature in this field, but in my opinion, if you are approximating the expectation by the mean value, why can't you approximate the joint expectation by covariance or something?
Well, that's what I explained as a second. Okay. That's done as a second order mean field. In second order mean field, we do this kind of an approximation, but then it rapidly gets messy. The second term you can do because then you have the covariance matrix. But what do you do with the triples? The triples is already getting a little bit annoying because how are you going to replace the triples by something which has a nice stochastic structure?
But if you're using covariance, will the triples come?
Well, you need to approximate the triples by your covariance matrix. And even the quadruples and the quintuples and whatever.
It's the same equation, but now you get the other terms.
Yeah.
Form. Start with the products.
Maybe I need to write it down to see.
No, it's a good question. I want to make sure others. I have one question, but I have, this is just the intuition. I have no basis to view it. But in your representation with eigenvalues, you have not used a sense of the separators in the graph. So the tree width graphs are very well-known graphs. Graphs have a very bounded size separator. One way that this could become a bounded size operator and won't unfold too often is when the separators in the graph is a bounded size separator, because then the effect will get quenched after the separator comes in and you decompose the graph off. And in that case, perhaps this equation, when we open it up, maybe it is doable because we have found that at least in some cases in tree bounded graphs, we can compute this probability of infection. I'm going to go and check what we have done. But maybe a good explanation for it is that this term doesn't keep going on and on. So if you have a graph and you split it into bounded size separators, not unbounded size. So that's it. And purely, maybe I'm wrong.
No. What you mean is you can have, is you're separating nothing else than what I call the cut size, because you have here the population of infected and not infected. And then the links in the cut set are those which transfer the epidemics.
A very small number of it's bounded size. So, and it continues recursively that way, right? And that's what three-way bounded graphs are. Planar graphs have row 10 separator. But it would seem to me that separator structure, basically this equation gets solved on a tree because in some ways the second order part will not occur. That's roughly what happens. And tree widths are just generalization of trees. People have done a little bit, and my feeling is your equation might give an interesting way to approach.
Well, probably we should do that. I don't know. That might be an interesting thing.
Something worth looking at. Just a good way to think about it.
I've not seen it yet.
Right. So thinking about this in the form of when the graph has certain recursive separator structure might tell you when this stalls basically is.
That might be an interesting problem.
So thanks for a very interesting talk. It's nice to see it all laid out so clearly. When I've looked at the impact of network structure on epidemics and tried to relate it to data, what I see is that there's this trade-off between the process parameters, your beta and delta, and the network structure, your eigenspectrum, for example. And it's so hard to identify a parameter from experiment in such a simple case that I wonder how we can go ahead and try to make these fine distinctions between that Weibull distribution you showed and the other distribution you showed that don't even show up until you're at times like 10 to the 20th or whatever was on the right-hand side of that graph. Do you see the problem I have? That it's just such a subtle distinction, and yet we can't make really basic distinctions like what is the true transmissibility?
I understand that measuring an epidemic is actually really confining. I think that's one of the weakest points. But once we measure a little bit more accurate, and not with a fraction of the population, but everybody in the population, I think that must be possible. I think we average today in data probably a little bit too much. We combine too much together, and I don't know what we actually measure in a population, or at least I think it's far away from the individual descriptions what I've given here, right? Otherwise, you can use NIMFA also as a meta-population model in which you say, well, I have the probability of multiple people like a household and not one single person. And then you average out a little bit, and then you have a little bit of hierarchical level of the population. And then probably I think that NIMFA or Markovian might be okay. The reason why I give it is because I was amazed by seeing how a Weibull of an other infection time has a very big impact. And in my opinion, an impact which might be larger than that of the spectral radius on the, well, we still need to do that in a good way to say what is the biggest impact. Is it the spectral radius or is it the alpha shape parameter in the infection? That's still unclear. But intuitively, I would say both of these components are more serious than I thought before. And that is basically the message that I'm giving. More I can say about real data distraction, because, well, I think you guys are much better in real data distraction than I am. So that's probably a weak answer to a difficult question.
That's a fair answer. I mean, Stephen has been epidemic modeling for a long time. So this question, the data is so noisy, unfortunately, that as you point out. Maybe we'll take the last question, Stephen, if it's okay. So I'll ask the question and we can answer his question. How does changing the waiting time distribution from exponential to something else like Weibull affect the memorylessness property of a stochastic process? In other words, he says, what can non-Markovian properties describe that Markov process in the graph can't?
That's precisely the answer. That's the history. What is actually strange, what occurs strange to me is that the total history of the infectional state in Markov theory does not affect, it's only the previous state. And then we take that for granted and we do all the predictions. Basically, the first paper in Epidemics, which I think it's a very serious paper, and which has been probably so many times quoted as the Karma-McKendrick paper, start with the first 8 pages on the real theory in which the history, the complete history in the past is taken into account. He comes then to integral differential equations, and that is a quite complicated paper, at least if you ask it to me, also conceptually. And that's why many people cite the paper and they just say, oh, that's the founder of the SIR model. Yes, their SIR model comes from that paper if you take everything constant and does not change over time. So the time event is ruled out, and then it reduces to that simple, reasonably simple sequence hyperbolicus or tangents hyperbolicus model of SIR. But the first 7 pages are still, for me, very triggering, but they are complicated. And to be honest, one of the approaches in my ERC approach is to try to get their way of thinking into a network setting, because that first paper has nothing talked about networks, which is basically amazing. And that might be another way of non-Markovian thinking on networking. So I have here I've here now used the fractional calculus that also came by an idea, by a coincidence, because I was talking with a colleague in Ernesto Estrada, probably you know him, and he is the editor-in-chief in the Journal of Complex Systems, and he was telling to me, "Oh, I'm now working on fractional calculus, and fractional calculus is great, or it's memory, and I take hysteresis and all these things into account. You should read it." And well, I start reading it, and I thought, okay, for epidemics, it might solve my Markovian stuff. That's how it goes. But now I'm stuck here, so probably we need another approach again.
Great. Let's thank Piet again. Wonderful talk.